Hello everyone, I'm Rajasri, Assistant Professor, Department of Electrical and Electronics Engineering, working at MLR Institute of Technology, Hyderabad. And in today's lecture, I'll be discussing single-phase half-wave controller. And here, half-wave controller, this we can also call it as unidirectional control. That is, only positive half cycle of the output voltage will be controlled, whereas negative half cycle it remains uncontrolled because we are making use of device called diode called uncontrolled device. We can also call diode as uncontrolled device. So that is the reason negative half cycle of the output voltage will not be controlled. Only positive half cycle we can provide the controlled output. And if you see here, we are making use of two devices in this circuit. One is thyristor and other is diode, where both are connected anti-parallel, and this anti-parallel switches are connected across supply as well as load. So here during the positive half cycle, here we are providing the triggering pulse for the thyristor 1, and we don't have to provide any triggering pulse for the diode. And this is the triggering pulse for the thyristor 1. And the moment when the positive half cycle has been appeared across the circuit, at that instant anode of the thyristor 1 is more positive with respect to cathode. That is how thyristor 1 is on, whereas diode, since it is reverse bias, D1 is off. So during the positive half cycle, only thyristor 1 will be conducted at the moment when we provide the triggering pulse. So right from here, the thyristor is forward bias, but at this instant called alpha, only we are providing the triggering pulse. That is how from this alpha, thyristor started conduction right from alpha till pi, till this instant called pi. And the moment it reaches pi, supply voltage, since it is 0, that is how later immediately negative half cycle has been appeared. And when negative half cycle has been appeared, the polarities across the circuit will be negative, positive. And because of such polarities, thyristor 1 will be turned off because anode is becoming negative with respect to cathode. T1 is turned off, whereas cathode of diode is more negative with respect to anode. So that is the reason here D1 is turned on. D1 is turned on, and that is how it is conducting current through the load. So during the negative half cycle, only diode 1 will be conducting current through the load, whereas T1 is remained turned off. So this instant called pi, our diode started conduction. From alpha to pi, T1 is conducting current through the load, and during the negative half cycle, D1 is conducting current through the load. So that is how we are getting the output voltage. Output voltage is due to the current flowing through the load, and since this is resistive load, where V0 is equal to I0 current flowing through the load multiplied by the load resistance. That is how we are getting the output voltage during the positive half cycle as well as negative half cycle, and this is the output voltage waveform. Coming to the output current waveform, I0, see, this is just similar to that of the output voltage. Output current waveform is just similar to that of the output voltage waveform, since I0 is equal to V0 by R. Only magnitude will be difference, or otherwise the waveform will be one and the same. So output current waveform will be just following the output voltage waveform. See, right from this instant called alpha, thyristor 1 is conducting. That is how we are getting the load current till pi due to T1, and the moment it reaches pi, what is happening? D1 is getting forward bias, and that is how, see, D1 is conducting current from pi to 2 pi, and this is the output current due to the D1. So if you see here, output current waveform is just similar to that of the supply current. Since I0 is equal to Is, that is because the same path. So that is the reason here Is is nothing but the output current which is actually flowing through the load. That is the reason here output current or Is one and the same. And here if you see, advantages. Talking about the advantages part, here we are having only two devices, only one SCR. So we will have to provide gate drive only for this particular SCR. That is how the control circuit is simple. Control is simple. Coming to the disadvantages part, if you see, only positive half cycle of the output voltage is controlled, whereas negative half cycle of the output voltage is just similar to that of the supply. We are unable to control the output voltage because we are making use of other device, so-called diode, which is uncontrolled device. So that is the reason here only positive half cycle is controlled. That is one of the drawback. And coming to the other thing, if you see, output current, supply current and output voltage waveform is not symmetric. So that is the reason it will have DC component, and this may saturate the transformer core because input will be connected to the transformer, and that is how it may saturate the transformer, as well as it will be damaging the loads which we are actually connecting to. That is, we may make use of induction motor loads, pumps. These will be saturated because of the presence of the DC component. And why is this DC component is actually present? It is because the waveform, output current as well as supply current waveform are not just symmetric. So that is the only reason DC component, it may saturate the connected load. So that is another disadvantage. And here, coming to the application part, this will be used for heating loads as well as lighting loads. That is, it is only applicable for the resistive loads because we have a limitation, so-called DC component is present because waveform is not symmetric. These are the disadvantages associated with single phase half wave controller. Coming to the derivation part, let us derive VRMS. Expression for RMS voltage, RMS output voltage as well as average value of the output voltage. Let us first see V0 RMS, where V0 RMS general formula is again 1 by T, 0 to T, V0 square of omega T, d omega T, whole to the power of 1 by 2. And here, let us check out the time period by seeing the waveform. See, here output voltage is conducting right from alpha to pi, that is half of the cycle, and the other cycle is pi to 2 pi. So both the cycles are not similar. That is the reason here we need to consider the time period as 2 pi, because every similar cycle is repeating for 2 pi, and it is actually conducting from alpha to pi, Vm square sine square omega T d omega T plus, and it is again conducting during the negative half cycle from pi plus alpha to 2 pi, is it not? It is conducting from pi to 2 pi. It is conducting from pi to 2 pi, and this is Vm square sine square omega T d omega T whole to the power of 1 by 2. And here let us take Vm square outside by 2 pi, and in order to integrate sine square, we need to write this in terms of 1 minus cos 2 omega T by 2, integrate from alpha to pi, plus again 1 minus cos 2 omega T by 2 from pi to 2 pi, and this is whole to the power of 1 by 2. And now let us take this denominator 2 outside, Vm square by 4 pi, integrating 1 we get omega T within the limits alpha to pi, minus integration of cos 2 omega T is sine 2 omega T by 2 within the limits alpha to pi, plus omega T pi to 2 pi minus sine 2 omega T by 2 within the limits pi to 2 pi whole to the power of 1 by 2. So here we get Vm square by 4 pi, substituting the limits upper limit minus lower limit, pi minus alpha minus sine 2 pi by 2 minus of minus plus sine 2 alpha by 2 plus 2 pi minus pi minus sine 2 pi by 2 minus of minus plus sine 2 pi. This is sine 2 into 2 pi is 4 pi we get. Sine 2 pi by 2 whole to the power of 1 by 2. And here we get Vm square by 4 pi. Further simplifying, pi gets cancelled. And here this term is 0. So we don't need to consider this. And this term is also 0. This term is also 0. So we get 2 pi minus alpha plus sine 2 alpha by 2 whole to the power of 1 by 2. And if we apply this whole to the power of 1 by 2, we get Vm by 2. Taking this pi inside, we get pi minus alpha plus sine 2 alpha by 2 pi, and this term is under root. So this is the final V0 RMS expression for single phase half wave control with R. Similarly, let us derive the expression for V0 average. V0 average is equal to, the general formula is 1 by t, 0 to t, V0 of omega t d omega t. And here the time period is one and the same, that is 1 by, here time period is 1 by 2 pi, and it is actually conducting from alpha to pi alpha to pi Vm sine omega t d omega t, where Vm is constant, bringing it out Vm by 2 pi, and it is also conducting from, if you see here, limits are alpha to pi plus it is actually again conducting from pi to 2 pi, pi to 2 pi Vm sine omega t d omega t. So here let us take this constant out, Vm by 2 pi, and integrating sine omega t is minus cos omega t, conducting from alpha to pi, plus, and it is again minus cos omega t, conducting from pi to 2 pi. We get Vm by 2 pi. Substituting the limits, upper limit minus lower limit, minus cos pi plus cos alpha minus cos 2 pi, minus of minus plus cos alpha, cos plus cos pi. We get cos pi value is minus 1, and here cos 2 pi value is 1. So here cos pi minus cos pi plus cos pi gets cancelled, and we get Vm by 2 pi into cos alpha minus 1. This is the final V0 average expression for single phase half wave controller with R load. This is V0 average expression. And in the coming up lecture, we'll be seeing single phase full wave AC voltage controllers. Thank you.